Alrighty. Okay, so let's go ahead and just get this divider thing done. Okay. Okay. We have a few operations. Do you guys still remember how to do it by hand first? Okay. So when you do it by hand, the first thing you have to figure out is how do we compare? How do we know there's 1 or 0 of the divisor of this portion of the dividend, right? Okay, that's the first thing you have to ask. And based on what you are allowed to use, okay, which is a subtractor, well, subtractors, and also and 2 gates, okay, you know, oh, well, maybe subtraction has something to do with it, okay. So what I'll do is I'm going to do this as a kind of more structured design. I'm going to go to project, add a circuit, okay, and I'll just give a name to this circuit here, okay. So I'll just say it's a division unit, okay, because it's really just a subcomponent. One thing I know is I have to do a comparison, and then based on the result of the comparison, I have to subtract that many of the divisor from the number that I'm comparing to. Is that okay? All right. So I'll just go ahead and do it. Okay. So it will require 2 inputs. Okay. Both are 4-bit wide. So we'll say 4-bit wide here. Duplicate this. This is another 4-bit wide thing. Those will serve as the input. And we'll also have 1 output, which is kind of like a 4-bit wide thing. So we'll have a 4-bit wide thing as the output. Okay. And in between, we know we have to compare. And we know that we cannot use a comparator. We have to use a subtractor for the purpose of comparison. So now we go to arithmetic. We pull a subtractor out. And make sure it's 4-bit wide because we don't need all 8 bits. So we'll just make it 4-bit wide. And we'll start with this, right? Okay, so the first thing we'll do is to say, well, we know we have to subtract these 2 numbers. So we'll just say, let's subtract these 2 numbers. We'll put the first one into the first input. We'll get the second one into the second input. And now we have a subtraction. But remember, we have to specify all the inputs to all the components. Some of the output may not be useful. That's fine. But the input, they all have to have, you have to specify something for the input. So in this case, I would use a constant of 0 to serve as the input. So we go to wiring, pick out a constant, and turn it into a 0. So that it is just a normal subtraction. There's no borrow from the previous subtraction. So we'll just go ahead and feed it here. And now we have a subtractor, which can also act as a comparator. Are we doing okay so far with this? Okay. So what do we use as the result of the comparison? Well, the output is not very useful because we are not, at this point, we are not interested in the difference just yet. We just want to know whether the second number is greater than the first number, right? And which flag is going to indicate that? The borrow flag. The borrow out is going to indicate that. Okay, that's good. So we know that this is going to be useful. But how useful? How do we make use of the result of the comparison? If the first number is greater than or equal to the second number, what do? We want to subtract it from the first number, right? But if the first number is less than the second number, what do we want to do? We want to subtract 0 from the first number, which means we need a multiplier, right? We need to multiply either a 0 or a 1 to the second number and subtract it from the first number. Okay, so let's do the subtraction first, the multiplier. We know how to do the multiplier from the previous homework assignment, which is basically just to go to gates. If you want to recycle your code from your previous one, that's fine, but I'm not going to do that. So I'll just go ahead and do this once here. So we'll say face south, 1 data bit, 2 inputs. So we'll specify 2 inputs, make it a narrow design, and we'll have 4 of these. 4, 1, 2, 3, 4. And we know how to multiply a 1-bit number to a 4-bit number from the previous homework assignment, which is what we're going to do here. But then we have to say, okay, which number are we multiplying? Well, another question is, do we actually need to do this? Okay, so there are two questions here. Okay, so I'll do it the normal way first, and then we'll try to figure out a way to optimize this so that we don't even need a multiplier. Okay. All right. So here's the multiplier. We know that 4 of these have to come from the second number, which is this one here. So now we need a splitter. So I'm going to do it the long way first. This is the long way to do it. So the splitter, I'll make it face south, break it all up. Okay, so the fan out is going to be 4, and then we have 4 bits here. And we're going to take, we'll type it from here. And basically just have those 4 bits feeding into each one of the AND gates. So one goes here, one goes here, one goes here, and one goes here. Okay, that's easy. But what am I multiplying to the other one? What am I multiplying to the second number? It's based on the result of the comparison, right? Because if the comparison says the first number is greater than or equal to the second number, we want to multiply by 1. If the result of the comparison is less than, then we don't want to multiply by 1, which means we want to multiply by 0. So we know the borrow flag is going to be useful because the borrow flag indicates whether the second number is greater than the first number, which is basically what we want, except it is opposite to what we want as a multiplier. So here you have 2 choices. You can either negate the input here, or you can just negate the borrow out before you put it into the AND gate. So I'm just going to do it the other way, which is to negate it first, and then just use this one wire to go into all of the AND gates. Okay. After this, if I combine the output out of all the AND gates, so I will just go ahead and duplicate this and flip it the other way. So we'll take this over here, make it face north. Then we can combine the output of these AND gates, which is the product. Okay, like that. And what do I do with the product of the second number based on how many of the output I should have here? I need to subtract that from the first number, right? Okay, so we'll have a second subtractor here. So the second subtractor is going to be pulling, oh, I can just duplicate this. So this is my second subtractor. So the second subtractor will still be using this as the first number. So let's pull this one all the way down here. That's the first number. And the second number is going to be the product of either a 0 or a 1 and the second number. And we'll put it here. A 0 into the borrow in just like before. And then the output of this becomes the actual output. Oh, I can make this look a little nicer by not moving things around too much. And we also need another pin as an output. So we have another output here, which is really just saying, okay, do we have a 1 or a 0 out of the NOT gate? Okay. So this is a division unit. Okay, it does most of the things that we need to do, except for padding zeros and stuff like that. Okay, but it does give us a result of 4 bits. It also gives us this 1 bit here. Where do you think this 1 bit should go as in the overall design? That's part of the quotient. This part here is part of the number that we'll be using. We'll be using 3 bits of this, okay? Because the most significant bit is guaranteed to be a 0 here. But we'll be using the least significant 3 bits of the output pin, the 4-bit output pin, and combine it with 1 bit pulled from the dividend, and then we'll do the same thing again. Is that okay so far? Sort of? Let's check whether this makes sense or not, okay? So we'll just say, well, let's try this with 1101, which is 12, divided by 7, okay? So what is this telling me? It's telling me 12 divided by 7 has a quotient of 1 and a remainder of 5. Does that make sense? Okay, makes sense. But let's go ahead and try to do it the other way, which is 4 divided by 15. 4 divided by 15 has a quotient of 0 and a remainder of 4. Does that make sense? Okay, so on a very small scale, this seems to be working. What this is not going to be able to take care of would be something like this. Okay, so in this case, it will simply say that there's at least 1 1 in 12. Okay, but the remainder still makes sense. Okay, because if you subtract 1 from 12, you have 11 left. Okay, so it still makes sense, except the quotient is supposed to be 12 and the remainder is supposed to be 0. But when we look at how the quotient, remainder, dividend, and divisor are supposed to work out, this still works out. Okay, it still works out. It's just that the quotient looks funny because it only has 1 digit. Are we doing okay so far? So I have just checked the design of the division unit, which is a subcomponent of my divider. And later on, we can come back and optimize this design a little bit, okay? Because there's a way that you can avoid the second subtractor. Okay, there's a way to avoid that using the conjunction. All right, so now we can go back to the main design and say, okay, now we want to carry out a 4-bit by 4-bit division. So once again, we need pins. Okay, so this one is 4-bit, the other one is 4-bit 2, and I'll label this one dividend, which is one of the inputs, dividend, and this one's going to be my divisor, 4-bit wide, and we'll call this divisor. There we go. And the output is going to be, there are 2 outputs, they're 4-bit, both are 4-bit wide. The first one is the quotient. So, and then the second one is our remainder. Like so. All right. So now the question is, well, what do we do with all of these things, right? The dividend is the one that needs to be broken up into tiny little pieces because we need to splice the individual bits, feed those into the division units, take the output, combine it with another bit from the dividend, and so on. So that means a splitter is inevitable from the perspective of the dividend. The divisor, on the other hand, for the most part, we only need it as a whole thing. We don't need to chop it up. So here's the dividend. We'll chop it up into 4 individual bits. There we go. And we can turn the orientation so it looks a little bit nicer. There we go. And draw some pins. There we go. There we go. All right. And if you remember how we did the division by hand, what we did was we take the most significant bit of the dividend, we pad 3 zeros to its left-hand side and say, okay, check this out. How many of the divisor do we have in that number? That's the first thing we did, right? So we'll do exactly that. So we'll go ahead and basically use another splitter, but this time it's actually more of a merger than a splitter. And we'll turn it the other way, turn it face north. And the least significant bit of this merge is going to come from the most significant bit of the dividend goes into here. And then we have 0 going into the other 3 bits because we are padding all the bits that are the most significant bits. So we'll use this one. Let's see. Okay, there we go. There we go. Okay. So now we have two numbers, right? Because we have this particular number, which is the combination of three most significant bits plus the least significant bit from the dividend, and we have the divisor. It's time to use our division unit. So we pull a division unit, and we stash it here. And the division unit is already having the right orientation, which means we put this number into the first input, we put this number into the second input, okay? Now the question is, what do we do with the output of this number? One is a part of the quotient, and the other one, we have to break it up, combine it with one more bit from the dividend, and then feed it into the division unit again, right? So we'll go ahead and do exactly that. And of course, I cannot remember which one is which one. I think this is the one bit that goes into the quotient. The quotient needs to merge four things into one. So I will go ahead and duplicate one of these things again. This time I'll make it face west so that we can merge into the quotient. So let's move the quotient up here a little bit. There we go. All right. So which bit am I doing right now to make this connection to the merger that we just created? Bit 3, that's correct, because this is the most significant bit of the quotient. So we say, let's go make the connection here. There we go. There we go. All right. What about the rest here? Well, we have to split it up, right? Because we have to split it up because the most significant bit of this result is not useful, okay? And we have to merge the output with one of the other bit, or bit 2 of the dividend. Now I know we have to do this split every single time, so I'm going to go back to the division unit and do the split over there, so I don't have to do it here. Okay, so let me go back to the division unit and change it a little bit here so that the output is no longer 4-bit wide but 3-bit wide. So we'll go ahead and get rid of this connection first, change this to 3-bit wide, because we know the most significant bit of the 4-bit number is guaranteed to be a 0. And we use a splitter, and this is the other way to use a splitter. You can have a width of 4 with a splitter, and you can have a fan out of only 1. And what you can do is you can specify the most significant bit is completely dropped. So this way, it's no longer technically a splitter. It is just throwing away 1 bit. Are we doing okay so far with this? Is that okay? Sort of? Actually, let me think about this. No, I'm wrong. I cannot throw away a bit like that. The subtractor has to be a 5-bit subtractor. Yes. Let me think. Now we're guaranteed to lose that 1 bit. Okay, let's revert all of these changes first. So undo, 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 undo. Okay. Just from looking at this, we know that we cannot, drop the last bit because this output has a 1 here, which means the subtractor needs to be a 5-bit subtractor because we have to take in 5 bits at a time to do the calculation. So I stand corrected here. And of course, it has to change everything to 5-bit wide. This needs to be 5-bit wide. That needs to be 5-bit wide. That needs to be 5-bit wide. And that needs to be 5-bit wide. This, oh, we need 1 more of these. It's not going to let me do this, is it?
Click on your splitter, and now shift-click on your
okay.
red.
Ah, thank you. All right, so we need. We have to redo all this stuff anyway. So we'll take all those out. There we go. And then we have to do the same thing here. It has to be a 5-bit splitter. Okay, that's better. Okay, here we go. But the main design is now, changed because everything is now 5-bit wide. Okay, so we need to give this one more 0. The divisor needs a 0 to be padded. This one, the divisor, the second number, can be a 4-bit number because we can pad the 0 in the design itself. So I'm going to change this one more time by changing this one to a 4-bit number. And we'll just pad the 0 as the most significant bit. Oh, we're missing one here. That. This one's 4-bit wide, 4-way split. You have to think about what you do in base 10, so it's not much different from what you do in base 10. Okay, so I think this is better. Oh, we need to do it here too. Okay, so 4, 4, that's a 4. Okay, this 5 that is having a problem. This is going to look really ugly, but it's... There we go. Okay, so let's double check to see whether this makes sense. We still have 12 divided by 1, and it says there's 1 in 12 with a remainder of 11. Okay, so it's still working out okay, except this is now giving us a 5-bit output instead of a 4-bit output. Okay, all right. So, but out of the 5-bit output, the most significant bit is guaranteed to be a 0. So out of this subtractor, this bit can be ignored. So we can now we can safely get rid of that one. So we can use a similar splitter to this one, duplicate it, except this time we are reversing it to face east. And we are only using the least significant 4 bits as the output. The most significant bit is guaranteed to be a 0. So this is now 4-bit wide. There we go. All right.
Shouldn't this still be 12 though?
Huh? No, it's not 12 because I can only have 1 bit as my quotient. I can only specify is there 0, 1, 1 in 12, or is there 1, 1 in 12? 1 is all I can account for given the width of the quotient. So that's why there's only a 1 here as the quotient, because I can only count up to 1. One divisor in the dividend. Okay. So it's still working. Okay, so back to main. Now we have to, this is okay because the input, one is 5-bit wide, the other one is 4-bit wide, and the output, this is part of the quotient. It is still correct. The next thing we have to do is to merge this bit with the output of this unit here. So we use a splitter for this purpose. Make it face west and 5-bit wide. We'll take the first 4 bits from one source, and we'll go ahead and take it back. The first bit is coming from one source. The 4 bits will be coming from the other source. There we go. I'm just trying to position it so it looks better. Okay, so now we take the output of this, put it into the 4-bit input, and then take this 1 bit here and put it into the 1-bit input of the merger. We replicate the division unit. This becomes the first number, and the divisor is always the second number. So the divisor is just going to be replicated throughout as the second number. There we go. And then we put this bit here as the second most significant bit of the quotient. And then we do basically the same thing again. Okay, so we have basically the same structure at this point. Are there any questions about this design? Can I partially check whether this design works or not? Yes, go ahead.
If I put my division as just 4-bit, is it okay?
Well, it depends on whether it works or not. Okay, so let's check whether this works up to this point or not, because I don't want to finish the whole design only to find out, oh, nothing works, right? So at this point, I can check already. Okay, what would be one case where I can check whether this makes sense or not? How about 1100 divided by 1? Would that help me check whether this design works or not? What is the result of 1100, which is 12, divided by 1? What is the quotient? It's supposed to be 1100, right? So in this case, I should have 1100 as the output if I were to test it like that. Okay, so let's check it. 1100 as the dividend and divided by 1. Okay, seems to work just okay. Okay, but what if I divide 1100 with 1, 1? That would be the same thing as 12 divided by 3. The answer is 4. And 4 would be 100 as the quotient, right? So let's check that, because I want to give it some test cases where I can see whether it works or not. Okay, that seems to be okay. I want to try next. I want to try 12 divided by 7. 12 divided by 7 is 1 with a remainder of 5. Now the remainder is not done yet. Okay, not even close. But I should have 1 as the quotient, and with only the most significant 2 bits specified, it should be 00XX, right? So let's check that. Okay, so now I have a reasonable amount of confidence that this overall structure is working. So I can now stack the rest of it. To stack the rest of it is really the same thing. Okay, so what we are going to do now is basically just to replicate the division unit and put one over here. The second input is always going to be the divisor itself. So I put the divisor into here. The other one is going to be a merge, just like the other one, of 4 bits coming from the previous division unit and 1 bit coming from the dividend. Stash it here. The output is going to another bit. That looks. Okay. This may look really ugly. I'm just trying to find out how to route this so it doesn't look too bad. It's gonna look kind of bad. There we go. And this goes to the other input, like so. All right. So I want to check this too. In other words, I want to find a quotient where the second least significant bit is going to be a 1. Okay? Give me one example. What would make the quotient a 2? What about 2 divided by 1? Wouldn't that do it? Okay, so let's check that. So go back into simulation mode. Have a 2 divided by 1. Okay, seems to work. 2 divided by 5 has a 0. Okay, so that seems to work too. 111, which is 14 divided by 1 is 14, and the quotient is the first 3 or the most significant 3 bits are correct. So every step along the way, I'm giving myself some test cases, so I don't go too far until I realize, oh, we have a problem here. Okay. Okay, so we'll go ahead and finish it with the last division unit. So we'll just go ahead and do basically the same thing. Replicate the division unit, and we'll take just like the other one. Okay, we'll replicate the splitter. The splitter is going to take most of the bits from the previous division unit. One bit is going to come from the least significant bit in this case. So this is going to look a little bit bad. Like so. And then the other one is just the divisor itself, which is coming from the divisor. Feed it here. And this particular bit goes to the least significant bit of the quotient. So we go all the way up here. I hope your design doesn't look as bad as mine. There we go. Okay, so right now we can actually see the quotient is correct. Okay, so far so good. But let's check again and give it a different number to work with. What about 14 divided by 3? Let's check that. 14 divided by 3 should be a 3. Should be a 4. Right, okay. Should be a 4 with a remainder of 2. Yep, go ahead.
I would suggest that you also attach the remainder so you can test that at the same time.
Yes, in this case I can now check the remainder. Where's my remainder? All this time I don't have a remainder, but now I do.
It's the output from the last division.
Yep, the last division unit has the remainder, so we'll go ahead and hook that up. And I'm going to make this a little bit better so I don't have to run wires all over the place. How about this? Does that make sense? 4 times 3 is 12. 12 plus 2, which is the remainder, is 14. Are we doing okay so far with this design? So the division unit really saves me a lot of space in the overall design because I'm basically saving everything that has to be replicated into a sub-circuit. And then I just reuse the sub-circuit over and over again. Are there any questions about this design? Yes?
So, if we were to have made this, but not as streamlined.
It doesn't have to streamline. Your design, can be completely flat, but it will be kind of bigger.
As long as it produces the right output.
As long as functionally it is correct, and 2, it is still playing by the constraints that I place onto this homework assignment, it will still be okay. It doesn't have to be optimal. Okay. Are there any questions about this particular design at this point? Now I'm going to optimize it, okay? Because there's one place where I can optimize. It is inside the division unit itself, okay? So when you look at the division unit, do you notice that there may be a chance I can make this simpler? One of the subtractor is not needed. Okay. Now, why do you think I say one of the subtractors is not needed? Think about what is fed into the subtractors. Okay. So when you look at both of these subtractors, the first number, basically this is a part of the dividend, is always going to the first input, right? And this is the same thing that feeds into the first input of the second subtractor. But they're subtracting different things. The first one is subtracting the divisor. The second one is subtracting a multiple of the divisor. So they cannot be merged. Right? It seems like they cannot be merged. But I can tell you they can be merged. Because you can always take, what about this pin here? What about this particular pin? The pin from the first subtractor is not used. Right? Let's see if we can use it. So what we're going to do now is to use this guy. And there is a place to put it. I'm just trying to figure out what is the best way to route it. Okay, well, just leave it here first. Okay. This is the result of a subtraction, right? But it is always subtracting the divisor from the dividend. So I cannot put this one as the output directly because sometimes this output should be, should be just the original, the first number, and not the version after the subtraction. Now I have to think about this a little bit. So we always have the subtraction here. Question is, the question is, how do I get the original number, which is this one, when I'm not supposed to do the subtraction? And other times, I want to use the actual result of the subtraction. Yep.
Well, on either side of the NOT gate, you have a 1 on one side and a 0 on the other. You could use those to determine those and a bunch of AND gates like you have on the left to determine which output you're going to use.
Kind of use it as a mux, right? As a multiplexer.
Yes.
But we cannot use multiplexers. We can only use AND gates. So this may not simplify the design. That's the whole point is, is it going to simplify the
That's
design?
how I did it.
Okay. So you basically use a whole bunch of AND gates as a multiplexer? That works too. I mean, that's fine. But I'm trying to figure out a way to do this so that it's not, it doesn't actually add more components to the screen. But it seems like it's not, I don't think it's possible to add more stuff to the screen. Because you have to choose between the difference and the original number. So that means you need a multiplexer. To implement a multiplexer using AND2 gates does not make the design any cleaner. So I suppose it can be done, but it doesn't really help to make it simpler. So I'm gonna give up that approach. So that's the answer. That's the solution. Well, one solution. Are there any questions about this solution? Yep.
Can you go back to the main?
Yep.
Can you see how you connected the remainder?
Yes. The remainder is actually just the output of the last division unit.
Thank you.
Mm-hmm. Any other questions? No other questions? Now, for those of you who want to have the minimum replication, in the main design, you can actually put this merger into the design itself. So you have one more 1-bit port, so that you don't need this merger before you feed it into the division unit. But that would be kind of like a splitting hair kind of optimization. So, any other questions? No other questions? All right. If there are no other questions, I'm just going to save this one and I'll upload it to Moodle. So this way you can download it and study if you want to. Call this divider. divider. And I'll put it into the homework assignment itself. Was it harder than the multiplier homework? Makes you think a little bit more? Yep. But now that you know the answer, do you feel better? I mean, now that you know how to do division using, hardware, logic gates, and only that? How many people here are planning to go into computer engineering? Well, this is the sort of stuff that you need to do, like day in and day out, because you are thinking about how to do all kinds of calculations in silicon, in logic gates. That's what computer engineering is about. It's not the programming side, but it's more on the hardware side, but it's kind of the interface between the two, because otherwise you'll be electrical engineering, where you deal with like transistors and the actual implementation of stuff. All right, so let's go ahead and put divider into here. So divider, load. So I'm saving this file into the description of the homework assignment. So for those of you who are interested, anytime you go to the homework assignment itself, you can download the solution now. The solution is a part of the homework. Any other questions? Did anyone other than him come up with a more optimal design? Because I'm interested in getting things more optimal. How many people tested the design like I did? You finish a part of it, you test it first, and say, okay, does this part make any sense? And then you move on. Okay, was it helpful? Did you find a mistake early on and go like, good thing I did not replicate this several times. And that's how you want to debug your programs too, in general. Any other questions related to this homework assignment? Nope. Okay, all right, well, I'm gonna stop the recorder and you guys don't have any active homework at this point, okay? I have not assigned the next homework assignment because I'm still working on it, okay? I made the register bank, I made the ALU, so I want to give you all the components and then you guys will have to kind of piece things together a little bit. Yep. Mm-hmm.
So the exam is next Thursday? Yes.
No, because I don't have a practice exam yet. So the usual things I do is I will give you...
There's a practice exam on Moodle.
Yeah, but it doesn't have all the elements that I want to contain in the practice exam, so we have to postpone it just a little bit. So because we haven't gone over the practice exam, so we won't have any... The actual exam is always 1 week from the day that we talk about the practice exam. And since we have not talked about the practice exam yet, it won't be next Thursday. It just means we're pushing more stuff later, right? I mean, it doesn't really help. But that's what we have, so you guys have a weekend that has no homework assignment. You can look at that.
Have a good weekend.
But there's a lot of studying, though. You have to read ahead of me and make sure that you get all the material.
Well, you say you have to be private.
Okay, see ya.
Are you still recording?
Yep.